See what happens when we take the derivative of a Laplace transform. So the Laplace transform is this function of big F here. Make it the derivative means this, because this is the definition of the Laplace transform. By the Leibniz rule, we can move this derivative inside the integral. We're taking the derivative with respect to s. Say it's the partial because there's two variables in here now. And this derivative is just minus t e to the minus st. Well, this is minus this thing, which is the Laplace transform of t times f. So we have a new Laplace transform pair or property. If I multiply a time function by t in the time domain, in the Laplace domain, it means taking the derivative and multiplying by -1. You keep doing this, and if you multiply a function by t to an integer power in the time domain, in the Laplace domain, it's taking that many derivatives and multiplying by -1 to the n. Here's a new property we would put in a table. Usual case for my students, just so we don't have to take too many derivatives and get too tedious, is where n is just equal to 1. You might want to write this down. And if we're looking for the time function, it would be this property here. The time function is -1 over t times inverse Laplace transform of the derivative. We'll get into a couple of examples of this. First, let's say this. Let's say you had to take the Laplace transform of this whole thing. And let's say you had a table that had at least this part in it, e to the minus at cosine. Well, you can see that it's just t times something in the table. By the property we just had, it means minus sign times the derivative of what was left, of the Laplace transform of what was left. Look it up in the table, and this is in it. It looks like that. So at this point, we just have to take a derivative. I'm not going to go through all that. With this. An alternate approach, say you didn't have all of this in the table. But remember, we had this property of if you multiply by e to the at of a time function, it's the Laplace transform of the rest of it evaluated at s plus a. E to the minus at evaluated at s plus a. And in this case, what's left over is t cosine 3t. Well, cosine would be in any table. So we're multiplying that by t, so now we're left with the same property again. It's minus the derivative with respect to x of just a cosine. And then when we're all done, we'll evaluate it at s plus 3 instead of s. So here's the Laplace transform of cosine of 3t. So now we have to take a derivative. I won't go through that. You get this. Substitute s plus 3 for s. You end up getting the same thing. So that's kind of how you go through this. If you can take a derivative, you can do it. You can dodge a wrench, you can dodge a ball. Sometimes you can go the other way. Let's say you had this, we've never encountered this before. Say your Laplace transform involves a natural log. What's the inverse of this? Well, the tip I give my students, if you see a Laplace transform involving the log or arctangent, think of this property. So let's take the derivative of this guy and see what happens. First, I can express the natural log of a quotient as this difference. Natural log of the numerator minus the natural log of the denominator. Then I can take the derivative of this guy. That's 1 over u du ds. The derivative of this guy is 1 over s squared plus 9, 2s, derivative of that guy, what that all is if you lay it out. And now from the property we just had, time function is minus 1 over t, the inverse Laplace transform of that derivative. In this case, it's minus 1 over t. This was 2 times cosine of 3t. And this was 2 times e to the minus t cosine. Distribute that minus sign, and here's the answer. You have to be a little careful going the other way because sometimes you can get an answer, but the time function doesn't really converge. It doesn't really have a Laplace transform. So you have to be kind of careful going the other way. Here's another example. Like I said, if you see arctangent, think of this property. So find the inverse Laplace transform of this mess here. And we will at least use a trig identity, which is given to us as a hint here. So again, think of this property. So take the derivative of this guy with respect to s. The derivative of arctangent is, let's see, 1 over 1 plus u squared du ds. So here we have the 1/2, 1 over 1 plus this whole thing is u squared times the derivative of that u with respect to s, which is this. And then do the same thing on this guy. Simplify it a bit by multiplying through to get this. And again, the time function is minus 1 over t times the inverse Laplace transform of all this, which is minus 1 over t times this. Distribute the minus sign, we have this. And at this point, we can apply this trig identity, and you have this kind of simplified time function. And actually, in the textbook I used, this was one of the pairs, one of the Laplace transform pairs. This was the time function. This was the Laplace transform. Right, that's that little property.